Okay, welcome back everybody. This is video 2 for AP Physics 2 Cram session. Again, I'm just going over mostly concepts here. And be patient if the videos are less quality than I usually have, but let's get started right away. Let's talk electric field lines. Okay, and we talked previously about this in our other video. Electric field lines start on positives, terminate on negatives. They are tangent to electric force vector. And you do not cross lines, so you can't cross lines. So, and we need to show some kind of connection to the charge value. So the first charge, let's say, I'm going to use these two here. Let's say I've got a positive 2Q here and a negative Q here. And we're going to draw some lines on that. Okay, so just remember that this is a plus 2 and that's a minus Q. So I'm going to erase that. So for clarity's sake, let's get started then. I'm going to draw electric field lines coming from the positive going to the negative. So let me draw one going straight across right there. And then one will wrap this way around. And another one will wrap this way around. Okay, and then since this is a 2 charge, let me just put a 2 there and a 1 here and a minus 1 here. I want to show twice the number of lines, so I'm just going to kind of show some of these lines going off, okay, into the distance there, trying to in search of other negative charges. So I've got 1, 2, 3, 4, 5, 6, 7. Now let me draw just one more line there. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 total lines, okay, drawn on this charge here. And maybe make it 9 and then 10. Okay, for this charge I can have a total of 5 lines on, so I'm going to draw one line coming in from infinity somewhere, and we'll curve this line into it here on this side, and maybe another line going on this side here. So these are coming from another charge somewhere else, we're not really sure where, but just in general, maybe from infinity somewhere. So this is a reasonable pattern here, not the most exact, but it should work. So notice how from plus to minus, that's where they are. And well, why is that so? Well, remember, for electric field, we pretend to put a positive test charge located in that region. So if I put like a positive test charge here, where would it go? It would go away from the positive charge here, and then it would go towards the negative charge over there. So just kind of a reminder what we're doing there. So let's say I've got 2 positive charges here, and from now on I will do equal charges. It'll make it easier. So a line will try to go over here and then get repelled away. And likewise, this line will try to go across and gets repelled away like that. And let's draw another line going like that. Another line. So we're showing repulsion. Again, notice how we don't cross lines at all. And just let me draw a couple more lines. I'll just draw 3 more lines on each one. And since we're doing symmetrical charges here, I must draw the same number of lines on each one. So there has to be some connection to the number of lines you draw and the magnitude of the charge. Since this was twice the charge of this one, I have 2 times the number of lines on this one versus this one here. But again, here we have equal lines drawn. Now what if we have 2 negative charges here? So we have a negative charge and negative charge here. Well, we're just going to reverse what this looks like here. So lines coming in from infinity going like this and ending on that one. Coming in this way and then ending on that one there. And likewise coming in and going that way. Coming in and going that way. And then I'll just show 3 more on each one. That one coming in there. And that should show a good pattern for you. So one more time, notice how the lines don't cross, and they are proportional to charge. Since these are the same charge between them, I can just show, the same lines on both. Now what about parallel plates? I mean, they're quite different. So if I have a negative plate here and a positive plate over here. Now remember, they do start on positives and terminate on negatives. But between 2 parallel metal plates, we're going to see a constant electric field across. So let me draw some lines straight across. Remember, electric field is the same everywhere between these plates. And that's a major advantage of having parallel plates. But at the ends, remember, we're going to get some curvature there. We're going to get some distortion at the ends there. Okay, and that's all I need to show there. So those are good patterns there to show electric field lines, okay, on charged objects there. But again, we have consistent electric field between these space here, but then at the ends we're seeing distortion. There's not consistent electric field between these charges. Those are point charges there. Now what about our rules for electrostatic and for metal conductors? So metals that are in electrostatic equilibrium. Let's take a metal surface here, just a metal block of some sort. And let's say I charge this thing negative. Well, first of all, the charges will distribute equally. I'll just draw a couple charges here. Okay, and they will reside on the outside. So that's rule one. So if electrons are excess on this particular piece of metal, if an electron tries to go in, it's going to get buzzed right back out there because they are repelling each other. So that results in electric field inside equal to 0. So I'll just say I'll put a 0 here. And the reason is if the electric field is not 0, then the charges would be moving. They would just redistribute themselves until the electric field, okay, became 0 inside the metal. So that's rule number 2. And then rule 3, I believe I talked about this one already. Electric field lines are perpendicular to the surface. Let me just draw some dashed lines here representing electric fields coming into this plate here. And I'm trying to draw them as perpendicular as I can. And again, if they're not perpendicular, the charges will redistribute themselves until they are perpendicular. Because this is a metal conductor in electrostatic equilibrium. So charges reside outside the metal. The electric field lines are perpendicular. Electric field inside is equal to 0. Now what that means is, and we'll talk electric potential in other videos, the electric potential everywhere inside this piece of metal is the same. And I'll show you how we actually calculate that in another video. So just so that there will be no motion of charges. If electric potential here was greater than electric potential over here, then charges would be moving. But this is in electrostatic equilibrium, so no charges move. Now what if I have a point here? Here's our last rule. So if I have a point, okay, versus a just, flat surface everywhere, we're going to find that charges will, congregate very quickly at the point. Okay, because again, they need to get perpendicular. Electric field's got to get perpendicular. Okay, so there's not the space for them to move around and in order to become perpendicular. So there's much more available space here, but when the radius of curvature is really small, there's no real space for those charges to move. So if we can congregate charges at points, electric field at this point is going to be very large. I'll just do big capital E there, and then it'll be smaller over here. So that again, those charges have to get away from each other as far as possible and make the electric field perpendicular. There's just not the space for it to happen. So electric field gets really large there. And this is kind of the nature behind lightning rods. Put these on your house so that, lightning sees a big electric field at those points and then avoids hitting your house. So that's an advantage, okay, for that rule there. Okay, so that's it for video number 2. In the next video, we'll talk superposition principle and calculating electric field and electric forces.